you are losing a lot of value if you can't make it, there's an enormous return on investment for any company that's paying a developer a reasonable developer wage and sends their developers here. I can't tell you how big of a mistake it is not to send someone to CppCon.
Okay, so welcome everyone. I'm Gabor. I'm working for Microsoft, and I will talk about lifetimes and memory safety in C++. But first of all, I would like to welcome everyone at the conference and encourage you to come to see us at the Microsoft booth, talk about the products, share your pain if you have some, so we can look into it and solve them, and join our Discord and take the survey. You can win various prizes. I wanted to give a short introduction. I started to work on Clang actually in 2012, and interned at various companies, including Microsoft, Apple, Google. All of them were compiler-related internships. And in 2018, I was working on the C++ core guidelines lifetime profiles. And I was working with Herb, working on both a Clang and an MSVC-based implementation. I also did a PhD in program analysis, and since 2022, I'm one of the co-owners of the Clang static analyzer. So I work on both Clang and MSVC. And lately in Clang, I also worked on a new data flow analysis framework together with some engineers at Google. They are using this framework for Krubit, which is sort of a re-implementation of Rust's borrow checker on top of C++'s type system. Okay, so during this talk, I will talk about some approaches to safety with a focus on static analysis. And I will highlight some of the changes we made to C++ recently to make it a safer language, because C++ is getting safer over time. And I will walk you through some of the tools that are available today, not just in MSVC, but also in Clang and GCC. And those can be useful and can be downloaded today. And I will also try to speculate on what will come next. I have a QR code in the corner. That's a link to the Discord channel for this talk. I shared some additional resources around memory safety with a focus on temporal memory safety. So in case you want to have some additional reading material, feel free to check those out. Okay, so let's get started. What I will not do, I will not tell you why safety matters, and I will not define safety. I will just wave my hands. And if you want to learn more about why does this matter and why, and how can we define it, you can watch any of the CPP Now talks in this topic from this year's conference. Or you can look into some of the documents different governmental and non-governmental organizations released around safety. And I will focus on memory safety. One of the reasons is that basically memory safety turned out to be about 70%. So 70% of the vulnerabilities we patch at Microsoft turned out to be memory safety related. And interestingly, this is not special to Microsoft. Google and Mozilla, they found similar figures. So it looks like even if you have like different engineering cultures, different products in different domains, memory safety issues have been a problem. So let's take a look what can we do about mitigating some of these problems. So we can talk about two kinds of memory safety problems. either like spatial memory safety problems or temporal memory safety problems. With spatial memory safety problems, we have out-of-bound accesses, and that is undefined behavior and can often be exploited. We have some mitigations for this. Buffer check is an internal tool at Microsoft. It's a static analysis tool that can find many buffer overflow errors. We plan to release it. It is a work in progress. Unfortunately, it is not available today. And it is using Cell, which is an annotation language, to describe some of the invariants, preconditions, postconditions regarding indices to make it possible to do function local analysis to find these buffer overflow warnings. We can also do dynamic analysis. We can use sanitizers. Address sanitizer has like multiple variants. Each of them has different trade-offs. Some are better used during testing. Some can be deployed to production. And I recommend you to use them and look into the differences between all the flavors. And we can also use bound check data structures. And there are some other language extensions like checkC that is like a buffer safe subset of C. And there are some recent proposals in Clang making C and C++ bound safe. So these are here for your reference. In this talk, I will mostly focus on temporal safety issues. So temporal safety issues typically use after free issues. For example, I allocate some memory. I have a pointer that points to this memory. The allocated memory is released. And after that, I try to read this memory through this pointer. And that's like a use after free bug. And sanitizers can often catch these temporal safety issues as well. But when it comes to static analysis, we have the core guidelines lifetime safety profile. I will talk a bit more about that later. We have Crubit, which is a work in progress, an experiment at this point. We have some static analysis warnings in MSVC's static analyzer. We have some warnings in Clang and GCC. I will talk about those as well. Cyclone was a precursor to Rust. It was an extension of C to make it memory safe. And there is an additional paper from SG23, which is a study group for safety and security in the standards committee. So the paper that was submitted to that study group. So let's talk about the different possible approaches to safety. Here, these boxes represent like all the programs. And we have programs that are safe and like do not have memory errors. That's the definition I'm using at the moment. And there are programs that are unsafe. And the black rectangle represents the programs that would be accepted by a static analysis tool. And we could go with an approach that I call safe by construction. Basically, we define a small subset of the language that is provably free of certain classes of errors. And then we are sort of restricted to use only those language features. But if we only rely on those features, we can get guarantees. And over time, we try to expand this subset, make this more and more, this sublanguage more and more expressive, hopefully accepting more and more safe programs. And the problem is we cannot grow this box big enough. We will always have some safe programs that are rejected by a static analysis tool that is following this approach. Another possible approach is to do bug finding opportunistically. So like the first version of a static analysis tool might accept all programs. And then as we make this static analysis tool better and better over time, it can find more and more errors. And basically making our use of the language safer and safer over time. Unfortunately, with this approach, we will always have programs that are unsafe, but the safety issues are not detected by this tool. And there is a theoretical results from decades ago that has the consequence that we cannot have a perfect tool. We cannot have a big black box that is perfectly overlapping with the green area on the left. We will always either have safe programs that are rejected or unsafe programs that are accepted, or maybe both. So let's compare these two approaches a bit. So with safe by construction, we get guarantees, like building software using this methodology will be free of certain classes of errors. And we can sometimes get around by the expressivity problem by providing escape hatches. And this is something that we have in C++ today. For example, the type system of C++ can already eliminate a huge class of errors. And we can use unsafe casts to get around these safety facilities if we need to. And similarly, in Rust, we have a borrow checker that would prevent us doing use after free errors, but we have row pointers that are not checked by the borrow checker. So that is like one way to get around these facilities. And the problem is with safe by construction, it is not, there is no free lunch. So basically, if you want to use this methodology and we have a big code base that wasn't written with this methodology in mind, we might need to re-architect the code base, and it is also somewhat harder to experiment in a code base like that, because maybe if I just want to do a quick and dirty hack to figure out if this API makes sense, I don't want to deploy this code to production, just do some quick experimentation. That can be somewhat a bit harder in a code base that is using this approach. On the other hand, with opportunistic bug finding, it is usually applicable to all code, and it is easier to identify false positives. It's easier to figure out what a warning is about, and we can make localized fixes, and we can roll it out incrementally. While with safe by construction, we might need to change APIs, and if we change APIs, that changes viral. We might need to update the whole software stack at once. So I wanted to show you an example where safe by construction doesn't really work if we want to keep the old APIs. This is a slide stolen from Chandler's talk from CPP Now earlier this year. So here we have a C++ API that creates a subspan of a span. And basically, this API cannot work in safe Rust. In safe Rust, an API like this would never be accepted by the borrow checker, at least not in a way it is used in this code snippet. So in Rust, we need an API that has a different shape, that works a slightly different way to do the same task. And this is just a small code snippet. Imagine if you have like a multi-million line code base, and suddenly you need to rewrite many of your APIs, and you need to stop using some of the STL. That's often not feasible. So one of the questions is, what can we do with code bases that cannot be migrated to a safe by construction approach overnight? And an alternative to all of this is to do both in a somewhat limited manner. So for example, when we see naked delete, we could suggest the user to use RAII instead. Or if we see use after free or some bad locking pattern, we can point out, okay, there is two unlock calls for this lock on this code path. Maybe you want to look into that. So basically this way, we can slowly migrate the user to use more safe facilities and make the whole code base somewhat safer. So this is a choose your own adventure kind of approach. So basically here, people can opt into what sort of code style warnings they want. For example, okay, I want to get rid of all of the naked deletes in my code so I can turn on those checks. And at the same time, the tool can find all of these bugs using opportunistic bug finding methodologies. Okay, so those are the like a big bird's eye view perspective of some approaches to safety. And now let's look into what changes have been done to the C++ language to make it safer. And I want to emphasize that this is not a comprehensive survey of all the ways C++ is safer today. These are just some of the highlights that are related to temporal memory safety. So let's take a look at this piece of code first. We have p, a pointer. It will point to local variable I. And this code attempts to read the value of I through p after the lifetime of I is ended. And this is a classical use after lifetime ends error. And if I call this function in a constexpr context, in MSVC, I will get the following warning message, or error message rather. So basically, MSVC can figure out that this read through this pointer it contains UB, and the code will fail to compile. And in fact, this is not specific to MSVC. You can try all major compilers, including Clang and GCC, and you will get similar error messages. So basically, one way to make our code safer is to migrate them to compile time. But I guess the best way to make code safer is to delete code, but the close second is to execute code at compile time. Okay, I wanted to highlight another recent change in the language. So let's take a look at this code snippet. We have a function that returns a string, and we iterate over the string in a loop. Let's see what this code would desugar to. And here there is a code snippet where we assign this temporary object that was returned by read input to an R value reference, and lifetime extension happens at this point, so that temporary will be kept alive for the full lifetime of this loop. So there is no dangling whatsoever. This is safe code. But let's look at a slightly modified example. Yeah, if you want to know more about the exact rules around temporaries, when they are created, when they are destroyed, this is one talk that you can go and watch. So let's take a look at a slightly different example. So here, read input might fail, so it returns an optional. And let's iterate over the result of this function call. So if we take a look at what does this desugar to, the value method of stud optional will return a reference. So basically, we bind a reference to a reference. So in this case, no lifetime extension would happen. So basically, the result of my read input will be destroyed by the end of the full statement, after the end of the full statement. So range will dangle. And this is a use after free error. At least it was before C++23. In C++23, the rules for object lifetimes changed. And this temporary will be kept alive for the full lifetime of the loop. So this code snippet is safe in C++23 and after. Okay, let's take a look at another example. Here, I have a tuple, and the tuple has a reference to a stud string inside it. And I initialize this tuple using an integer literal. And here, the compiler will insert a conversion. So basically, the conversion will create a temporary std string object, and the reference will be bound to this temporary std string. And this temporary std string will be destroyed after the statement, so the reference inside the tuple will dangle. And this paper introduced a couple of new type traits. These type traits are not something that you would see in application code. This is like an advanced tool for library developers, and library developers can use this to basically make this code ill-formed. So the code that was basically a runtime error before, or UB, is now ill-formed and would not compile. And this was also voted into C++23. So these were a couple of cases how C++ got safer recently. And this trend is probably going to continue. And let's move on to the tools we have today to find temporal memory safety issues in our code. Okay, so first I will talk about statement local lifetime analysis. Basically, maybe the code examples I showed you previously hinted at that, but dealing with temporaries in C++ can be somewhat error-prone, and yeah, the rules can be confusing. So these statement local lifetime checks are focusing on trying to identify cases where these temporaries are misused, and those cases result in some kind of temporal memory safety issues. And one would think that seasoned developers might not make these mistakes, but that is not the case. When we first implemented these statement local lifetime checks, we found errors in many real-world code bases, including LLVM itself. So compiler developers, people working on the C++ compiler can occasionally also make mistakes like these. So these are really easy to make. So let's take a look at this code example, and let's focus on this line. So basically, we create a string view, and let's zoom in. And let's take a look at the types. So in one of the branches, we have a string literal, and on the other branch, we have a std string. And according to the language rules, we need to convert both of the branches to have the same type, and this conversion will create a temporary object. So we will end up initializing the string view with one of these temporary objects, depending on which path do we take. And these temporary objects will be destroyed by the end of the full statement. And we will end up having a dangling string view, which is bad. So we have a couple of warnings in all major compilers to catch cases like this. And what I want to emphasize, all of these warnings are slightly different. For example, this particular error is coded by Clang and not coded by GCC or MSVC. But I have other examples that are, for example, only coded by MSVC and not coded by Clang or GCC. So basically, the more compilers you can use, the better. And hopefully, over time, all of these differences will disappear, and all of the compilers will catch all of these tricky cases. Yeah, and one caveat here, while I'm talking about statement local lifetime analysis, I'm not sure whether W-dangling reference in GCC is statement local, because I'm legally not allowed to read GCC code base because of software licenses. So that's take it with a grain of salt, but I'm very confident about MSVC and Clang because I implemented this check in both. Okay, so let's focus on the checks I'm familiar with in Clang and MSVC. There are a couple of examples that are caught by these statement local checks. For example, here, it is showcasing that it cannot only catch like temporaries in some statements, but in some cases it can also catch cases where I return a reference, for example, to a stack local variable. And yeah, that also happens occasionally. And the last example is one example that is not coded by Clang today. Basically what I wanted to emphasize here, these checks are on by default. So if you compile any code with a recent version of Clang, this warning, the -w dangling GSL is on by default. So Clang will diagnose some of these temporal memory safety errors. And in case of MSVC, we don't have these warnings in the compiler, but they are enabled by default in /analyze, which is a static analyzer built into MSVC, but it is not part of the regular compilation. On the other hand, this is on by default in the background code analysis in Visual Studio, so people would get the green squiggles. And in case people use code analysis in Visual Studio for C++, this is part of the default rule set. So this is something that we already ship in multiple tool chains. So let's take a look at a couple other examples. So previously, what I showcased, those examples used the STL. And it is easier when we deal with the STL because we know how the STL behaves. Like the compiler can understand those types. But what about like user-written types and user-written functions? If we do function local analysis, then the compiler might not be able to tell what the user-written function is doing. But even if we can do interprocedural analysis, maybe the called function is in a library where I don't have the source code, or maybe it's a system call and I'm not analyzing the operating system kernel, and so on. So basically, sometimes we need to teach the compiler what is going on behind the scenes, and lifetime bound annotation is one way to do that. So let's look at this code example. So basically, if we focus on the highlighted line, we create a temporary object, and we will bind this temporary object to the formal parameter of function f, and we will return a reference to one of the fields of this of this temporary. And what will happen? Basically, this temporary object will be destroyed at the end of the statement, and this reference will dangle. So note that these two pointers have different values. They are pointing to different memory locations. On the other hand, they are somehow related. They are related in the way that if one of them is dangling, the other is also dangling. And basically, this is what the lifetime bound annotation describes. If I add lifetime bound annotation to this argument, to this reference, the meaning of this annotation is that the returned reference has the same lifetime as the formal parameter of this function. So basically, teaching the compiler what is the dependency relationship between these references can help the compiler diagnose more issues. And this code, after adding the annotation, is diagnosed in MSVC and Clang. And this doesn't only work with row pointers and references, this works with string view and other user-written types. And this is a more complicated example where we have multiple functions chained through, like we have multiple calls chained. And basically here we have two literals, integer literals. And when those integer literals are used in this context, we will create a temporary integer from these literals. And these references will bind to the temporary. So this, the first line of this function will potentially produce references that dangle. So basically, after we added the annotations to the min and the pass-through functions, MSVC will be able to detect these dangling issues. So basically, the lifetime bound annotation is implemented in Clang and MSVC today. Clang had it for a long time. We added it to MSVC relatively recently. Okay, so after the statement local analysis, let's move on and look at more complicated cases, because sometimes the dangling cannot be detected by looking at a single statement at a time. We need something more, we need an analysis with a bigger scope. So looking at this code example, we can do some data flow analysis, and initially string view is invalid, meaning that we cannot look up or cannot use the subscript operator to look at the characters of the string view. We can take this branch, and if we take this branch, the string view will point at a static string literal. So basically, the string view in this case, the static string literal outlives the string view, so it is safe to use the string view in this case. So after this branch, there are two possible ways to get to this program point. We could either take the branch or fall through. And in data flow analysis, in case we are flow sensitive, we take both opportunities or both options into account. So in this case, we represent that the string view is either static or invalid. And then there is a condition, and there is a use of string view later on, like looking at the first character. And the question is whether this use is safe or not. So what is the challenge here? The challenge here is that we might have no information about how the two branches are correlated. Maybe I only take this branch, this second branch, when the first branch was taken. And if that is the case, then this code is safe. If that is not the case, this code is not safe. So basically, there are two potential approaches to this problem. We could be the optimist and say that, okay, it's probably fine. It can be fine, so the developer knows what they did. And we can be a pessimist and say that, okay, it might go wrong. I'm not entirely sure about it, but if I'm not certain that it doesn't go wrong, I will emit a warning. So basically, when we are doing opportunistic bug finding, the optimist approach is better. It's more user-friendly. It will only point out real issues, while the pessimist approach is better at providing guarantees, if that is our goal. If you want to know more about the differences between these and how we made the lifetime analysis more optimistic to define the high confidence lifetime checks in Visual Studio, I recommend you to check out this blog post. So the optimist is erring on one side, the pessimist is erring on the other side. The question is, could they agree in some cases? And in case we look into this, let's take a look at this first code example. There is a dereference of this pointer, and the question is whether this is safe or not. And this depends on what G is doing. If we are doing function local analysis, we cannot look at the body of G, so it is pretty hard to come up with a precise answer. So the optimist would say, okay, G might return a valid pointer, so it can be fine, so I don't warn. A pessimist would say, okay, but what if G returns a pointer that is null or invalid? In that case, this code is not safe. So the pessimist would warn. And in some cases, we might be able to help the analysis by introducing additional annotations. This is an annotation from Herb's lifetime safety profile. And here, basically, it would describe that the lifetime of the returned pointer is the same as the lifetime of the first argument. And since the first argument is alive at a point where I dereference P, then it is safe. So basically, sometimes when the optimist and the pessimist disagree, we can add an annotation and make them agree and get a precise result. Unfortunately, that is not always the case, but I will talk more about that later. So let's look at another example. So here, again, we dereference a pointer. Is it safe? Is it not? It depends on what G is doing. And G might initialize this pointer to be a valid pointer, or G might just leave it uninitialized. And in that case, it would be unsafe. So again, the optimist would not warn, the pessimist would warn, but we can make this precise by adding an annotation. And in this case, this is a cell annotation that basically tells the compiler that G will initialize the argument to be a valid pointer. Okay, let's look at this last example. So here we return a reference. But basically, this reference is a reference into stud vector. And that vector might have been invalidated by the pushback before the return statement. Is it a problem? Is it not? It depends on how we use this function, because maybe the caller always reserves enough memory that this pushback never invalidates the buffer of the vector. If that is the case, then the use of this function is safe. If that is not the case, then this is unsafe. And unfortunately, in this case, we do not have any annotations today in any of the proposals to describe this potential invariant. But this is like not the only case. So we cannot always make the optimist and the pessimist agree using annotations, at least if we are using a constraint annotation language. So basically, if the optimist and the pessimist always agree, then we have the perfect analysis tool that only accepts the safe programs and rejects all of the unsafe programs. And basically, the consequence of Rice's theorem is only that we cannot do that automatically. But we might get to that if we require additional input from the user. And in some cases, we can come up with relatively simple annotations like these to make the user able to communicate these invariants to the compiler and make the analysis precise. In other cases, we would require the user to write like SMT formulas, and we would need to use theorem provers. So even though it is theoretically possible, it's probably not practical for everyday use. And I wanted to briefly talk about other lifetime adjacent checks. So some people would consider unwrapping an empty optional or using an object after it became moved from lifetime safety error. And we have specialized checks for these cases, basically in most of the tool chains. Like we have a check for unwrapping empty optional in MSVC. There is an experimental check for that in Clang tidy. And we have a use after move check in MSVC, and we have a use after move check in Clang tidy, and we have a use after move check in the Clang static analyzer. So in this case, Clang actually has two. And in fact, many of these tools, for example, the Clang static analyzer has very good opportunistic checks to find lifetime errors and null pointer dereferences, use after free, double free, and similar errors. And the Clang static analyzer can print these nice traces that show you what path needs to be taken in the source code for the error to happen. So basically, the morale here is the more tools you use, the better. Some of these tools are more opportunistic. Some of these tools are more optimistic. Some of these tools are pessimistic. And basically, you can pick the right ones for your code base, and hopefully over time, like we can start with the optimistic tools that are more forgiving, and we can migrate and use more and more pessimistic tools and making the code safer and safer. Okay, so these were some of the tools that I wanted to talk about. These are all available today. I know integrating those into the build system might not be easy, and it has some costs, but I definitely think that we can benefit from using this tool and adopting them more widely. We might not get guaranteed safety from them today, but we are getting safer over time. And in the final section of the talk, I would like to take a look at what might come next. Making predictions can be challenging, especially about the future. So let's take a look at MSVC first, what is coming next, and what are we planning to do. So I want to emphasize this is not really a roadmap. Like the term I use here is investigations. So we are looking into these items, and it is we will see how many of those will actually get productized. So first of all, we are interested in closing the gap between the different statement local lifetime checks. It would be nice to get consistently good results from all of the three major compilers to catch all forms of local dangling, especially when annotations are available. And also, we plan to move the high confidence lifetime warnings out of experimental. Also, currently, the flow-sensitive lifetime checks do not support the lifetime-bound annotation. This is something that we might look into. Yeah, one of the interesting points about annotations and the different approaches of like using the optimistic or pessimistic tools, if you use an optimistic tool and you add more annotations, the tool will find more errors over time. On the other hand, if you use a pessimistic tool, adding annotations, describing like the invariance of your code is a way to silence errors, is a way to convince the tool that the code is fine. And of course, the question is, can we add the wrong annotation? And can that like hide real errors? And the answer is sometimes. It depends. So for example, when I add an annotation that is incorrect, if the analysis can see both the function call and the function body, it might be able to detect that this annotation is incorrect. If it doesn't see both, then it is possible for that to be undetected. And other languages have the same problems. For example, in Rust, if I have a foreign function and I'm using the foreign function interface to call into C or C++ or some another language, in the Rust function, I might need to define the lifetimes of the references if I want to provide a safe API. But the Rust compiler has no way to check if the code that is outside, that is not visible by the Rust compiler is actually compliant with those contracts. So we want to compare different approaches, the different competing approaches out there for temporal lifetime safety. And Herb is working on CPP2, and he plans to revise the lifetime safety profile as part of that work. But if we want to take a step back and look at C++ instead of only looking at MSVC, we might see that there are multiple approaches, like the core guidelines lifetime safety profile. We have a paper in SG23. There is Krubit, which is basically overlaying Rust type system, part of Rust type system on top of C++. And there's Hilo, formerly Vel. I'm not sure if that is the correct pronunciation. Hopefully someone can correct me if I'm wrong. That has mutable value semantics. Whale is a different language that has a different approach. We have Swift, another safe language that has its own take on the law of exclusivity. Basically, we have many potential approaches, many potential avenues to getting safe or getting safer. And the question is, which is the right way to do it? Which is the right way for C++ to do it? Might not be clear at this point. There are certain common traits of these systems. For example, limiting aliasing through mutable references is like one way to deal with some of these problems, but there are different approaches. Like Rust is doing this at compile time in most of the times. Like Rust has also facilities to enforce the borrow rule at runtime, but that's for a different talk. And on the other hand, Swift has a hybrid approach. In most of the cases, it can detect problems when we have multiple mutable reference to the same object at compile time, but it will also generate runtime checks when it cannot validate that the code is safe at compile time. And it's quite interesting that Swift actually introduced these runtime checks in release builds relatively recently. So it looks like there are examples in language ecosystems where they gradually made the language stricter in some ways, and the ecosystem didn't explode, which makes me a bit more hopeful about what we can do in C++. And one question people might ask, where is my Tony table? So how can I experience what is it like to write C++ using some of these models? And this is something that we unfortunately don't have today, at least don't have today publicly. Maybe at some companies, some people already have some versions of this, but as far as I know, they are not released yet. And we always have the option of building something new from scratch. Because we are engineers, we are excited about coming up with new solutions, reinventing the wheel. So I want to do a small thought experiment, trying to make C++ safe using a type system-based approach. Specifically, I am following this blog post, which summarizes some of the methods to use the type system to make a language memory safe. But first of all, I would like to talk about this code snippet in Rust. And specifically, I want to talk about what unsafe means in Rust. More specifically, I want to talk about what unsafe does not mean in Rust. So basically here I have a local variable and I have a row pointer, R1, that points to this local variable, and I have a reference or a borrow that also points to this local variable. And in the unsafe block, I use both the row pointer, the reference, the row pointer, and I'm using the borrow or the reference. So basically, dereferencing a row pointer in Rust is an unsafe operation. It can go wrong in a sense that the compiler doesn't check that this is safe. So unsafe means it's not checked by the compiler, it is checked by you. But what unsafe doesn't mean, unsafe doesn't turn off any of the safety checks in the language. So in case I use a borrow in an unsafe block, that is still checked by the compiler, it is still safe to use that borrow, and it is still guaranteed with some qualifications, but it is still guaranteed that I will not have a use after free error. I will not have a temporal lifetime error. So using this insight, I want to talk about GSL span. So GSL span is bounds checked. And with GSL span, if you use GSL span, it is always bounce checked. So you cannot put an unsafe block in your code turning off the bounce checking. If you want to avoid the cost of bounce checking, what you can do, you can convert this GSL span into a row pointer, or you can convert this into std span or some other data structure. So basically you can introduce conversions between types. And you can do conversions from a safe construct to an unsafe construct or the other way around. So basically in Rust, if we think about the way we delineate safe code and unsafe code, is not by using unsafe blocks, but by using the type system. Depending on what kind of types am I using, that operation is either safe or unsafe, and in the same expression, I can mix safe types and unsafe types. And basically the code in the unsafe block is still checked, at least for the safe types. So basically, following this approach, we can add new facilities to the language that would introduce, for example, affine and linear types. And this is challenging, but can be done. And basically, those types cannot be misused as far as the lifetime goes. And since only using linear types is not ergonomic, we can introduce some second-class simplified references that are guaranteed to be safe. And basically, using this small subset of the language, we can build up code that is safe by construction, and we can gradually introduce more and more safe language features that makes this subset of the language more and more expressive, so we can write more and more code using this subset. And what I didn't need for this thought experiment, I didn't need profiles, and I didn't need unsafe markers. I only needed the type system, and I can, in any function, I can mix safe and unsafe facilities, and I can look at the types to figure out if an operation is safe or unsafe. And this is like the best possible migration experience in some sense, because I can take a function and just change the type of a single argument, fix the compilation errors, and the code became somewhat safer. So basically, I don't need to convert a lexical block at once. I can do one expression at a time if I want to. And if you attended the talk, the keynote earlier this morning, I agree with Bjarne that a language like this would no longer feel like C++. So some people would wonder, is this something that we should invest in? Should we come up with a new language from scratch, basically, almost? Or should we just use Rust if we want these safe by construction facilities and focus on the interop between Rust and C++? And should we, instead of trying to come up with safe by construction methods, figure out how to harden the code that is not safe by construction that we have today, how to basically come up with cheaper ways in terms of development time to make old code that we cannot re-architect safer. And basically, these are valid questions. Unfortunately, I don't have answers for those, but the more people trying to tackle these problems, the better. So I would like to invite all of you to think about safety and potentially experiment with some ideas and share your experience, write blog posts, come to SG23 and share your perspectives. So that would be a great help to the C++ community. But at the same time, I think C++ is getting safer over time. I sampled just a couple of ways how the language got safer. That's like not. So there are many, many, many more proposals that actually made C++ safer. That was just like a small selection of them. And we have a wide variety of solutions that we can use today. Some of them are dynamic, some of them are static. And with static analysis, we can use pessimistic and optimistic approaches. And hopefully, as the tools are getting better, maybe we can get more of a choose-your-own-adventure style of tooling, where you can start with optimistic tooling and turn some dials gradually, make them more and more pessimistic, making your code safer and safer, giving a migration path to a much safer language. Even if it is not safe by construction, maybe for practical purposes, we can get close enough to safe by construction that basically it would be fine. And we would no longer get all of these reports from different organizations to move on to use safer languages. Okay, so once again, please enjoy the conference. Come and talk to us on the Discord server. Do not forget to fill out the survey. You can win nice prizes. And there are a couple of other sessions we have at the conference. Feel free to check them out. And in case you have any questions, there are a couple of mics at the front. We should have a couple of minutes for them.
Hi, thanks a lot. Great talk. You mentioned that there are cases where annotations might be incorrect. And if the compiler sees the call site and the implementation of a function, it can help. With modules, there's less of a partitioning between header files and implementation. Are there any considerations or thoughts about maybe adding these annotations automatically to the BMI, so to speak, and or making
definitely.
BMI some indications of what types of analysis activity is inside the module?
Yeah, so basically I think it is possible to make everything work with modules as well. And we definitely plan to add all of these annotations to the BMI when we are doing static analysis. And basically, when the annotation is incorrect, it could be incorrect, like the problem might be detected in the function definition or at the call site. In case the problem is detected in the function definition, we would detect this problem when the BMI is generated. So in case the same warnings are not turned on when the BMI is generated, that could be a potential way to miss problems. But basically, we can include a lot of information in the BMI. We could, for example, include that what warnings were enabled when the BMI was generated. So we could potentially emit a warning. Okay, there is a warning that is enabled at the call site that is using that particular annotation, but that warning was not enabled when the BMI was generated. And if that is the case, we could potentially, so this is not something that we do today, but I think there is a path to get safety, to get safer using modules. So I don't think there is a problem there.
And thanks for the talk as well. This may not be the main focus of this talk, but at the beginning, you had this example where context for context would, in this case, a use after free would be reported, but in a regular non-expert context, it would not be. Can you maybe elaborate on this a bit?
Yeah, so basically, the standard requires the compiler to catch these sort of undefined behaviors when the code is evaluated at the compile time context. So any compiler that is conforming to the standard is forced to catch these. There might be some sort of undefined behaviors that are not caught by some of the compilers today. But if that is the case, that is a bug that you should report to to your vendor, and hopefully they will fix it. I'm not sure if that answers your question.
I was mainly wondering why in a non-expert context it would not be reported.
Oh, I see, yeah. So in case, for example, function f is a const expr, and I not const eval, that would mean I could call this function in a non-const expr context, and in that case, the compiler is free to evaluate this function at runtime. And in case this function is evaluated at runtime, basically we have UB. In that case, it is not guaranteed that any sort of checks would take place. So whenever we run a function like this, whenever we call a function like this in a non-const expr context, unfortunately, we will not detect these errors.
Thank you very much.
Thank you for the talk. I have a question. In Rust, the semantics of references are underpinned by the idea of you either have one mutable reference or many shared ones. And this rule set guarantees the safety, or does much of that. Are you aware of any other rule sets that also work with borrow checking that way, but that are different, that still provide safety?
Yeah, so basically this idea that you either have sharing or mutation is, and they are being exclusive, is very common, but they can be enforced many ways. So even in Rust, for example, there are library facilities where you can sort of delay this check to be done at runtime. So basically, yeah, I don't recall the name of the library facility at the moment, but even in Rust, if the borrow checker would reject your code at compile time, you can just use a different kind of, almost like a smart pointer that would be accepted by the borrow checker and would do this checking at runtime. So this idea is very common, but there are multiple flavors. How is it implemented? Whether you can get to safety without the borrow rule, I think that was the core of your question. I am not entirely sure. You could always do full program proofs without enforcing the borrow rule. So the great thing about borrow rule, the exclusivity of sharing and mutation, is that it is relatively easy to enforce at compile time compared to other alternatives. So I think it is possible that we can enforce safety using other rules that are not the borrow rule, but those are likely to be harder to enforce at compile time.
Thank you.
Okay, the session is over. Thank you very much, and see you around.